Please welcome Travis Cardwell, who's going to talk to us about C bindings. Take it away.
Thank you very much. Today I'm talking about automatic C binding generation for Haskell. This is a project that I'm working on with my colleagues at Well-Typed. And I'll introduce the project soon, but first I'd like to sort of explain why foreign function interface is important for Haskell. I think we'd much rather use Haskell. We have safety and types. But foreign function interface is very useful in Haskell for a number of cases. One of them is to interact with other software. So on your system, if you're running your window manager or something, you need to use foreign function interface to interact with that software. You may want to use foreign function interface to use audited or trusted implementations. For example, cryptography software is notoriously hard to implement, so using an audited library is usually a good idea. And it's also useful for interfacing with existing implementations. Maybe FFmpeg is not what your core logic is, so you can just use FFmpeg to implement these video transformations and work on your core logic in Haskell. And then perhaps later, if you have time, re-implement FFmpeg in Haskell if you want. So creating and maintaining FFmpeg bindings can be pretty tedious. Haskell and C are quite different. With C, you have to worry about memory management. The C types are quite different. And when you're implementing the Haskell, there's a lot of boilerplate to implement these kind of bindings. So we're trying to improve on that situation. So today I'd like to introduce hs-bindgen. hs-bindgen provides fully automatic generation of Haskell FFmpeg bindings from C header files. And the design of this library is, or the design of the utility is based on these core design principles. The first is automation. We aim to produce bindings without user input. You can always use overrides to configure how bindings are generated, but that's not required. Our goal is that for most cases with sane C projects, you can just run this and get Haskell bindings that you can already use. We also strive to preserve semantics, both in explicit and implicit semantics in the C code. I think Haskell distinction of types and being able to provide instances for new types, for example, is very powerful. So in C, you usually have typedef, type aliases that are the same thing, but we want to be able to preserve those semantics where needed. And we also want to provide predictability so that code generated by hs-bindgen is clearly predictable from the C code, and that's just to make the tool much easier to use. Given some Haskell code, it's easy to understand where that's coming from. So I have one motivating example here that's quite simple. This is a point_h header file that defines just a data type, struct point, and a function, print point, that perhaps prints the point to the screen. So these are just very small two declarations in C. What do you have to do to create Haskell bindings for this? So first, you have to have a data type that corresponds to struct point. You have to implement a storable instance for that type so that you can marshal the memory from between the Haskell and the C world. You have to write a C wrapper function that is compatible with the Haskell FFI. So here, you'll notice that the print point passes a struct point by value, and Haskell CFFI requires passing arguments by reference. So Haskell CFFI cannot use this function directly. So generally, you have to write your own wrapper function to work around that limitation. And then you need to write a Haskell function that corresponds to this print point, that allocates the memory and calls your wrapper function. So here's how I would write manual bindings for this case. So this is the header file that defines this wrapper function. So since this is a static inline, both the declaration and implementation can be implemented in the same header file. Here we have a function wrap print point that takes the argument as a reference, and then it dereferences that argument to call the actual print point function. Then implementing the Haskell code, this example uses the hsc to hs library, which I'll explain on the next slide. But you can see that it defines a data point type that very closely corresponds to the C struct point. It's pretty straightforward to just translate the code over, but writing it by hand for all the types can be pretty tedious. Then you need to implement a storable instance. Here is where the hsc to hs tool comes in handy. The storable instance has to have the size, alignment, and the offset of fields for your type defined, and that is all platform specific. So when you're using hsc to hs, it runs C code at build time that finds the correct constants to insert into these hash locations and creates the correct Haskell bindings for your current platform. So then we also have a foreign import call down here, and this is a call that imports the wrapped print point function. So you'll notice on the previous slide that we have a hash include point wrappers.h, and this is importing from hash include point wrappers.h wrap print point for the pointer API. And then finally, we can write our print point, which uses the foreign with function to allocate memory and call our print point wrapped function with that pointer. So even though that we only have 2 declarations in C, this is a lot of code coming out. And you can see why I chose a small example. hs-bindgen can generate all of this code for you. So I'm skipping the common imports, but here hs-bindgen generates this data point, which is very close to what I would write by hand. You'll notice that the names are all generated automatically, so the users do not have to specify the names. And then the storable instance is also very similar. You can see that it's generated code, so we're using lambdas and de Bruijn indices. But the constants are all coming, all defined in the generated code. This previous slide is an example of the types that are generated, and then we also generate submodules for functions. So we have unsafe, safe, and function pointer submodules that allow the user to decide what is the appropriate way to call your C functions. And here we have a C API add C source template Haskell function at the very top. This embeds this generated C code that's shown below. So this is also very close to what we write in manually. It's just a function that takes a reference to a struct point and dereferences it to call the actual print point function. There's a lot of, I thought I knew C very well before starting this project, and I've learned that there's a lot more that I didn't know. And there's a lot of devil in the details. And so you'll notice things like these hashes. There's like limitations on the C length of identifiers and things. And C headers are all in one single namespace. So there's all kinds of details that require these kinds of tricky implementations. Okay, so all of this code is generated by hs-bindgen. You don't have to write any of this, and you can just use the library. So as a brief overview of the architecture, hs-bindgen is designed sort of similar to a compiler. We have a front-end pass that incrementally processes and annotates a C AST across multiple passes. This is using the trees that grow style annotations. And then we have a backend that has It takes the final AST from the front end and then translates that to a Haskell AST, transforms that to a simplified version, and then goes through the preprocessor or template Haskell backends for code generation. So today I plan on going through a few common questions that will sort of illustrate the design of this project, and then go through one case study. So first, the big question is, how are the C headers parsed? We use libclang, which is part of the LLVM project, to parse the C headers. So this library parses the C headers and exposes a libclang AST. So then we can traverse that AST and create our own internal hs-bindgen C AST. One interesting thing to note is that this is the only pass that is using I/O. All the other passes are pure. So we have to use libclang to create the initial AST, and then we have pure passes that can iteratively refine that AST and generate code. And it's libclang that determines the sizes and alignment of types and the offsets of fields So LLVM is a targetable compiler. You can pass the target architecture. And so hs-bindgen allows you also to specify a target, and you can generate bindings with the correct size, alignment, and offsets for different architectures. The naming is a very critical part because it has it's one of the very user-facing sides of the project. So to name, we construct what we call a use-def graph. And this example is a bit convoluted. It contains many anonymous structures. In C, you don't have to name structs. But the reason why I chose this example is to show how the names are nested. So this example has an anonymous struct that's defined on line 1 that's used by reference in the typedef top level. So we have a graph that shows that this :1 is our initial representation for anonymous structures. It's just like the source location is used by typedef, used by ref in a typedef. And then inside that, we have 2 anonymous structs that are used in fields of that outer anonymous struct. And they're used by value, inner1, inner2. Then there's one more internal anonymous struct. Given this use declaration graph, we can assign names to the anonymous declarations. We use the @ to denote anonymous. So this anonymous struct on line 1 is denoted as struct anonymous top level underbar deref. And you can see here how as you go into the nested declarations, you just sort of add underscores and suffixes to show exactly what the name is. So one slight detail is that in C, each struct has its own namespace. So you can't just have simple C name to Haskell name, because you'll have collisions all the time. That's why you have to go through such hoops to name anonymous things. And these default naming rules are not customizable. This is to support predictability. You use these names when interfacing with the system, and being able to easily guess how the name should be makes it easy to use. And then, of course, these names have to be mangled to create Haskell names. That's relatively straightforward. There's differences between Unicode, like valid names in C and Haskell, so there's lots of details. But in general, you just take the C name and so the names of types and constructors have to have a first letter that's uppercase, while other names have lowercase first letter. Excuse me. But there's many cases where you want to customize generation. So we have a data type called a binding specification that describes your Haskell bindings. And this single data type is used for 2 purposes, one of which is this guiding generation. So we call prescriptive binding specifications. They provide a way to provide fine-grained customization of how bindings are generated. So for example, you could use these to customize which Haskell names are used, which instances are derived, which are generated, as well as what the representation of different types is. So for example, sometimes you want to have a type that's opaque. So these binding specifications are exposed to users as either JSON or YAML files. And this is an example of customizing a name using a YAML file. So here we specify that some type named linked list that's exposed by header example H needs to be given the Haskell name linked list in Pascal case instead of with the underscore. So these binding specifications can be generated, and then so you can generate your binding specifications and then customize them. Or if you want, you can write them by hand. So for example, if you have a library that has types that you want to use in your bindings, you can write binding specifications to make sure that those bindings are used. The second purpose of binding specifications is compositionality. This is the same file format, but the use is different. So we call these external binding specifications. So they allow existing Haskell types to be used instead of generating new ones. So a simple example is a library that has a network, HTTP, and TLS component if you were to generate bindings for HTTP and TLS separately and include the network types, then each module for HTTP and TLS would have separate and distinct definitions of the types. So those aren't composable. You can't use them together. So instead, first, you would generate bindings for a network module. And while doing that, that generates the binding specification. And then when you generate bindings for the HTTP and TLS modules, you use that generated specification file as an external binding specification. And that ensures that the types are imported from the generated module. Since the generated modules have the same types, they can be composed together very easily. And again, you can write them from scratch. One other complication in generating binding specifications, or in generating bindings, is to determine which parts of a library you want to generate bindings for. And to solve that, we have selection predicates. This allows users to select which declarations to include or exclude from generated bindings. So we have you can select and exclude based on the header path or the declaration name. In addition, we implemented program slicing, which allows users to select transitive dependencies. So for example, I have two very common examples here. One of them is that you have some kind of library that you want to create bindings for, but you don't want to select all of it. You just want some subset of the library, because it's a very complicated library. You can use the selection predicates to choose which part of the library you want to select, but you also need the dependencies of that part of the library. And if you had to create selection predicates for every single dependency, that would be very hard to first determine and then maintain. So you enable program slicing, and then all of those are included by default. And second, it's very useful for also including bindings of including the dependency types. So if you want to create bindings for one whole library, but it also has dependencies, and you don't want to have separate libraries for all those dependencies, you can use program slicing to pull the needed types of all the dependencies into your library. Before I mentioned that types can be made opaque, and program slicing also takes that into account. So if you create a prescriptive binding specification to make a type opaque, then program slicing will not pull all the dependencies of that type. Macros are a very complex case because macros are handled by the C preprocessor. And so LLVM can tell us where macros happened, but it only tells us the result of the macros. So in hs-bindgen, we have to reparse the underlying tokens and create our own implementations. So there's three cases of macros that I'd like to cover today. The first is constants. This one's very trivial. If you have a hash define, on the left we have an example with an integer, on the right is a double. We just create a direct binding for that type. You'll note that these names are not very pretty. In C, it's common to have constants as all uppercase, but in Haskell, we have to have our first character lowercase. But this is all done on purpose because it's better for us to understand where the names are coming from than to have to memorize the complex translation rules. Another case is for types. So a hash define can also be used sort of like a type def. In this example, there's a pointer int, which is a type for a pointer to an integer. And we translate this to a new type wrapper around the underlying type. This is done to support the preservation of semantics. And then expressions are much more complicated. In this example, we have a C macro that defines a function reg pointer that takes some argument that's named pointer and then adds 12, some constant 12 to that pointer. And the name of the argument indicates that this is probably a pointer, but it's not typed. So in Haskell, we need to generate an appropriate polymorphic function that's a translation of this C function. And to do that, we use type families to model the C semantics. So here, this specific function uses the add type class that has two type parameters that indicate the type, the first of which is polymorphic, and then the associated type add result is the result for your specific platform, because all of this is platform independent. So per platform, we have different C semantics, and the type classes are generated accordingly for your platform. So if you pass a pointer, reg pointer will return a pointer. If you pass an int, reg pointer will return an int. And finally, I'd like to talk about a quick case study. This is the PCAP, packet capture C library. It's a really old but well-tested library. And this is an actual command used to generate it, so it exposes some of the details. We have to have GNU extensions supported. We want to select all of the library, but PCAP library has some deprecated functions inside of it. And if we select those, then you might get linker errors. So we have a select except deprecated predicate as well that can use the C annotations to automatically remove those deprecated functions and avoid those errors. And we're outputting to the source directory into a module named generated.pcap. And this library takes about, so all of the type module as well as the function modules together take about 156,000 bytes, covering more than 4,000 lines of code. A lot of it's very straightforward, but I wouldn't want to write it myself. hs-bindgen is a nice way to create these, or at least bootstrap, for if you want to be able to maintain them yourself. Here's an example usage, which you don't need to read through. This is just the most interesting usage that I could make that would fit on the screen. This finds all device names using the PCAP find all devs API. And this illustrates that it's still C. You have lots of memory allocation. We're traversing a C linked list. And this is an example of our low-level API that we're currently working on. And in the future, we're going to work on more higher-level APIs to make this a little bit more palatable. We also generate Haddock documentation. So here are the excerpts from the find all devs and free all devs functions. The PCAP library does not include any documentation in the headers, but we generate documentation that tells you the C declaration, where it's defined, and which headers it might be exported from. If there is deoxidation documentation, we translate that to Haddock as well, and then also attach these additional information. So I hope that some of you are wondering how soon can I use hs-bindgen. I know personally I'm very excited to start using it in projects. We're currently working on the low-level API, and we have a release coming soon, so please check it out and try it. And we have a plan to create a high-level API as well to make it more easy to use for Haskell. Thank you.
Okay, we have about 8 minutes for questions. Plenty of time.
When you bind a function, the function can be pure or impure.
Yes.
And if I have a sine or cosine mathematical function, yes, and can I control it's not IO double is the result of the function? Can I get some control of that?
Yes, yes, we support having pure functions as well.
This is great stuff, and I would like to use it, but then I noticed that this is not really Haskell, it's GHC Haskell.
That's correct.
And now I'm sad.
I have two questions. One is about the user live clan. You mentioned that you use for the hs-bindgen.
Yes.
So do you actually somehow bootstrap the usage for live clan so that it generates the hs-binding for live clan?
We've considered that, but we're bootstrapping it manually. So we have a separate function, separate smaller core that uses. It will go through the C header file and generate our libclang bindings. But it's not hs-bindgen itself.
I see. And the second question is that how do you deal with the C name length limit, like as you mentioned?
Right.
I mean, if there is a length limit for say some specific number, but if there is a nested struct, then it will easily go over the length limit.
So those nested C names are all internal. They're on the Haskell side, the hs-bindgen side. And we only have to worry about the C name length when we're generating functions, because we have to generate those wrapper functions that are in C. And so for those, we use hashing to ensure that there's a constant fixed length of the functions.
I have an actual question. Can you go back to the thing that had the reg-putter macro?
Which macro?
That one, yes. Now, if that was actually the macro, then that is not the right thing there, because if I use that macro, reg-putter with some p, and then it says ×3. When you expand that macro, that ×3 will be applied to 12 and not the whole thing.
So you would like to have, for instance...
So I'm just wondering, do you recognize that if macros are sort of used in a weird way, where it's you're actually using the token pasting rather than used it as a function?
That's a good question, and I'll look into that further. First, we implemented our own ad hoc macro parser, because we have to look at the underlying tokens given by libclang, and we have since been re-implementing it to use an existing Haskell library for parsing these things, and I will check.
I mean, I don't see what you could do if that was the actual macro.
Right.
But I would like to be told that.
That would be very nice.
Deal with it.
Very nice feedback. Thank you.
Thank you very much for the talk. I've actually used the tool a little bit. Edsko got me onto it when I was complaining about C things in the past. In my previous job, I committed some horrible sins in the C preprocessor using X macros, but functional X macros, which pass macros to macros. And I was wondering if this had any chance of being able to make any sense of much more complicated uses of the C preprocessor than... it's a relatively simple function, but if it took in other macros, is there any chance that could be type checked? I'm not even sure that there is a type that could make sense for those usages I have.
Yeah, for macros, we're covering like the simpler cases first, and I think we can handle pretty complex functions, but if there's something that we don't know how to do, we just fall back to the expanded version. And if you have any test cases for us, we can try.
I can give you some horrific ones if you'd like.
Yeah.
Hi, Travis. Great talk, great tool. You mentioned that it's target specific. So you either have implicit or explicit in the generated code. I was just wondering, do you record the target, the implicit or explicit target you're generating the code for in the target specific files?
We do not currently, but that might be a very good idea. Yeah. Thank you.
So we'll have two more questions, one to the left, one to the right. Richard, I think we're going to have to pass you.
Why not use duplicate field records for the structures and overloaded the dot extension?
We are looking into doing exactly that. Duplicate field and overloaded dot. We're looking into it.
Yeah, that would be great. Thank you.
Thank you. So at Cubic, we built a tool with a similar purpose that generated outlang stubs. And one problems we ran into was C pragmas, underscore, underscore, something, underscore, underscore. Right. There seemed to be any number of those, and every time we upgraded the operating system, the header files would get new ones that our parser didn't yet cope with. You haven't mentioned those. I just wonder whether maybe you don't suffer them in the same way that we did. Or
yeah, there's a lot of pragmas, and so currently we're supporting muscle, there's a libc and muscle, and we're trying to test on Linux, Windows, and Mac OS. And we have a fixed set of architectures that we're currently testing, and we're just testing extensively and trying to cover those cases because there's always things that pop up. And Yeah.
You can just ignore most of them.
Yeah, yeah. And in addition, like LLVM gives you a whole list of built-in macros at the very beginning. So every single file even if you're not importing from some standard library, you get this huge set of macros that you have to support. So it's a challenging problem. Thank you.
Yeah, one last question over there.
Yeah. I think twice during this presentation you talked about predictability of names, and I'm wondering, I don't really get who or what that predictability is for, because you know, it seems like you already generate this documentation which maps the names to their Haskell version.
Yes.
And people who are unhappy with the names are probably going to change the underlying C source or do some hack anyways. So I'm just wondering if you could comment on what the predictability you're talking about is.
Yes. So the names are also used in the predicates. So if you want to select, you need to specify a name that's our name after we name anonymous declarations. And in addition, in the binding specifications, which are used to specify to describe the bindings you want to generate, or for external bindings, these also have the C names in there. And we did experiment quite a bit. In the early stages of the project, we had ways to say, please generate more Haskell-like names. And in the end, we determined that it's not worth it. And it's better to have a very, very predictable, simple version, and then allow you to customize when needed. But thank you.
Excellent. That's all we have time for. I see there's a lot of raised hands still. So meet Travis at coffee, and yeah, please thank him, man.